Okay, this is a Matlab short on generating tones and filtering the result. Okay, along the way we're going to talk about making an FIR filter with the FIR1 command. Okay, so let's get started. In step one, what I'd like you to do is make two tones. I want one of them to be 500 hertz, the other to be 1000 hertz. I want 2 seconds of duration for each tone. Okay, I want 1 second of silence between each of the tones. And to do any kind of sample data system, I have to choose a sampling rate. Let's make that 8,000 samples per second. Okay, so let's get started. The first thing I'm going to do is clear the Matlab workspace and then enter the sampling rate. FS is 8,000 samples per second. And then if I wanted 2 seconds of data, I would need 16,000 samples. Okay, so I'm going to start at 1 and go all the way up to 16,000 in steps of 1. All right, from there, I can generate the two tones. All right, so I put in the cosine. Here's the frequency, 2 pi 500, and then I replace T with N divided by Fs because it's a sample data system. All right, so I do that for both cosines. One's at 500 hertz, one's at 1000 hertz. And then I make a bunch of zeros to insert between the two. So I wanted 1 second of silence, so I need 8,000 zeros. There's a zeros command in MATLAB that will generate that for you. From there, I just push everything together. Okay, so that's one nice thing you can do in MATLAB is you can easily concatenate vectors. All right, so we push those together to form one big vector and call it X. All right, so we're ready to listen to the result. Okay, so I can evaluate this. It's going to be pretty loud, so if you're wearing earphones, you might want to pull them back a bit. So if we evaluate this, we're going to run it first. Okay, so if we evaluate this, we get two relatively loud tones. Okay, so the next thing I want to do is I want to filter to remove the 1000 hertz tone. Okay, so I have this as 600. Let's change this to 900 because if you had a cutoff of 900, that should do the job. All right, so let's go ahead and try it. All right, so that designs the filter. The next thing I want to do to be aware of is how to plot the impulse response of a filter. Well, for an FIR filter, this doesn't apply for all filters, but for an FIR filter, you can plot the B vector, and the B vector corresponds exactly to the impulse response. So if I plot this, I get the stem plot that shows the impulse response as a function of time. Okay, notice it looks like a shifted sync function. And that's why I wanted you to plot it, because sometimes when I'm designing filters and I want to make sure I got it right, I plot the impulse response because I know basically that a low-pass filter impulse response looks like this. Okay, so file that away in your memory banks. All right, I also want to look at the frequency response of the filter. We talked about in class that you can use the freq_z command. It will give you, you put the B vector in, you put the A vector in. The A vector is 1 for an FIR filter. You tell it the number of samples. I'm going to put 1,000 frequency samples. And this is optional. You can put in the sampling rate and it will come back with analog frequency on the horizontal scale. If you leave that off, it's going to use normalized frequency. Okay. All right, so let's evaluate freq_z. And we get this plot. A bit, make it bigger. All right. And so our question would be, how much attenuation is there at 1000 hertz? So we can use this data cursor thing to try to look. So there's 996, and at 1,000 we have almost 30 dB of attenuation, minus 29.7. Okay, so that's going to reduce the sound, all right, but it's not going to completely eliminate it. You'll still be able to hear it. Okay, so let's run this. Okay, so the next step is let's apply the filter and get an output. All right, so our output's going to be called Y out. We're applying the filter. We put the B vector in. We put the A vector in. And then we put the signal that we're trying to filter in. All right. So let's do these all at once. Let's apply the filter and listen to the result. Okay, so you probably heard a loud tone that made it through the filter without too much distortion. And then you heard the softer tone that was 30 dB down from the original. Okay, so let's plot this and take a look. All right. I'm not sure if this is what you were expecting. That's what I expected, because I knew I was plotting signals that oscillate relatively quickly. Okay, and I was plotting all the values. All right, so if you zoom in, here's a zoom trick. Okay, so click on the plus button, then right-click your mouse. Okay, look for the zoom options and do the horizontal zoom. Okay, so there we can now zoom in horizontally. Okay, and what we see here is the tones. All right, so what I want you to notice is the green is the filtered signal. Right, notice there's a little bit of delay going through the filter. So the blue is the original. Here's the green. There's a little bit of delay that happens when you go through an FIR filter. We'll learn more about that in the class as we go along. Okay, so this green part is the original, along with the blue signal. You know, the original is the blue. The green is the filtered result. It looks like one big green blob because the green got plotted on top of the blue, right? So this is what I would have expected to see. All right, we can zoom in to the filtered portion. Okay, zoom again. All right, and what we see is the original signal. Okay, and we see a little bit of filtered signal still making it through, and that's the part we can still hear. All right, so if we wanted to make this a little bit better, let's go back and take a look at this cutoff. We cut this off at 900, so that was, if we only wanted to keep the 500, we could be a little more aggressive on cutting things off right after 500. Okay, so let's put this at 600, and let's recompile this filter. Let's also look at the freq z command to see the frequency response. All right, so zooming in, we can look at what happens at 1,000. Right, and we see that we get 56 dB of attenuation if we move that cutoff frequency back closer to the 500 hertz. Okay. All right, so that's not unexpected. All right, so let's now reapply, listen, and look at the plot. All right, so you may have still been able to hear a little bit of the signal after it was filtered, but it's substantially reduced. And if you zoom in, you zoom in here. This is times 10 to the minus third. This is a really small results still getting through the filter. All right, so there's some practice with applying filters, and what I'd like you to do for this assignment is repeat all this, only this time add a third tone. Okay, so it should be 2 seconds long. It should be a second of silence between the second tone and the third tone. Instead of using a low-pass filter, use the help on FIR1 to do a band stop filter that will still eliminate the 1000 Hertz tone, but let the 2000 Hertz tone through the filter without much attenuation. Okay. From there, what I want you to do is upload the time domain plot of the original signal overlaid with the filtered signal. So here's the plot I want you to do, only with 3 tones instead of just 2. All right, so we should talk about how to export a plot. So what you can do is go File, okay, and we're going to do Save As. All right, and what works well for the things I want to do with Canvas is to export this as a PNG file. PDF doesn't work as well in Matlab figures, so let's do PNG. We can call this filter output, and I'll save that to my desktop. Okay, and that should have exported it. Okay, so do that exporting of the figure plot and then upload that to Canvas to satisfy the requirement for this Matlab short.